Okay, so this movie is meant to be sort of a bridge in between the more popular science summary of low mass star formation and the more technical information that you need in order to start doing science with star formation data. So we showed this cartoon a lot in the popular science summary of low mass star formation, but this is, of course, the popular science cartoon. Let's get into some of the more technical details. One of the major concepts that you need to understand star formation is the concept of blackbodies and spectral energy distributions. So you may or may not be familiar with blackbodies. In textbooks, you get graphics, sometimes like one or both of the top. Here we've got intensity as a function of wavelength. This is a different textbook that's plotting power as a function of wavelength. In both of these cases, they haven't given you any units on the intensity or the power. And then the wavelength is quite explicitly linear. And I don't quite know why they've done that. Maybe because they think people can't understand logarithmic scale. But, whatever. I mean, there's tons of bad things that have come out of the pandemic. But one tiny, tiny silver lining is that people are now much more familiar with logarithmic axes. So look at how quickly that peak changes. Most of the time when you're thinking about blackbodies, you're going to plot logarithmic axes both on the x and the y because these things change rapidly. Now in this plot, we've got visible light going here. In this case, the blackbodies are peaking redder. In this case, the blackbodies are peaking bluer. But this is how we're going to be familiar with blackbodies. We've got the axes here. It's log in both x and y. This is wavelength on the x-axis and spectral energy on the y-axis. Now, when you plot it in this way, okay, on this side, the functional form, the mathematical expression of this side was first described by Wilhelm Wien in 1896. So this side of the curve is called the Wien side. This side of the curve, in contrast, was first described by Lord Rayleigh and then a little bit later by Lord Rayleigh and James Jeans in the early 1900s. So this side of the curve is called the Rayleigh-Jeans side. It took them a long time to understand how to connect that side with this side and to come up with the mathematical form that describes this entire shape. Okay. So now, before we even get into it, let me make this clear. Stars can be thought of sometimes as blackbodies. But all SEDs, all spectral energy distributions, are not blackbodies. If I knew why people made this mistake, I would teach it better, but I don't know why people make this mistake. So let me just warn you, all SEDs are not blackbodies. So when I make this curve, this is a blackbody curve because I have defined it thusly. I made that mathematical definition and I plotted the mathematical definition. So that is a blackbody. But when I plot actual data from a star, it's not a blackbody, it's an SED. Blackbodies can be represented as SEDs, but all SEDs are not blackbodies. If it helps, think of it as a Kleenex facial tissue thing. All SEDs are not blackbodies. All facial tissue is not Kleenex. Maybe that helps. An SED, remember, is a spectral energy distribution. There's energy density as a function of wavelength or frequency. Astronomers, and for that matter, media offices, sometimes get sloppy, and they plot either brightness or energy as a function of wavelength and still call it an SED. But technically, an SED is a spectral energy distribution, which is energy density as a function of wavelength. So here's some press release images. In this case, we've got brightness as a function of wavelength. You can see there, it's explicitly logarithmic on both axes. Now, on the top, we've got a plain star. There's the blackbody curve representing the brightness from that star. Here we've got a star with a continuous dust disk. The dust goes all the way into the star. So here we've got the gray is that SED from the plain star. That colored SED is the net SED of the star plus the dust disk. So that infrared excess is that infrared emission that comes from the dust surrounding the star having been heated by the star and re-emitting that energy as infrared light. Here we have a star with a dust belt around it. Now here the two gray lines are the two SEDs from up here. The colored SED is this object's SED. So we've got something that looks like a black body to a certain point, and then you get what amounts to a second black body, because we're making the assumption that all of that dust is at the same temperature because it's roughly the same distance from the star. So it's like adding a second black body at a cooler temperature. So this kind of bump and wiggle in this case comes from the fact that there's a gap. Okay, so these two objects have infrared excesses. This object doesn't. There's no dust around it. These two objects do. This is a white dwarf with a disk around it. This emission comes from the white dwarf. This comes from the disk. And those dots are the spectral energy distribution. The smooth lines are the model fit to it. This is a much hotter central object than the young stars we'll be working with, but it still is an object with an infrared excess. This one, here we have the dots are the data. The smooth lines, the continuous lines, that is a model star. You can see right away that it is not a black body because it's got bumps and wiggles. It is not a black body curve. It is a model star, and it is being fit to the data. This, however, is a black body. That is a model disk. And you can see that that model disk starts to contribute measurable flux above the star after about, well, that's K-band. This is IRAC 1. So somewhere between K and IRAC 1, it starts to matter. And you get these kind of the subtle infrared excess. This is a much more subtle infrared excess than that is. That is whopping big, unmistakable, large infrared excess. This is a much more subtle infrared excess. And in fact, in order to notice that this star has an infrared excess, you have to do careful modeling. You cannot assume that the star is a black body in order to detect that this has an infrared excess. You have to know quite a bit about the central star. In this case, this is a close binary. So you have to know quite a bit about both stars in order to do the modeling of the stellar emission in order to figure out that there's an excess at all. This press release image is looking just at the infrared portion of the SED. So here again, we've got the same sort of three that we had at the very beginning. We got a star without dust, a star with disk that goes all the way in, and a star that has a disk with a hole in the middle. This is just looking at the infrared portion. So there's the Rayleigh-Jeans slope. Here, there's bumps and wiggles, but it's flat. And then when you've got an inner hole, it matches the star out to a certain point, and then it comes up for an infrared excess. Now, we're going to start leaving the popular science and the cool graphics regime. This is from a journal article, so it's not nearly so slick, right? Here we've got cartoons of what the star plus disk is doing. Here we've got a true spectral energy distribution. Here I've got log of lambda f sub lambda. So it's truly a spectral energy distribution as a function of wavelength. This is plotted in a log. Here we've taken the log before plotting, so both axes are logarithmic. This is a cold black body. In other words, you cannot see the central object at all. It is entirely enveloped within its cocoon, and that cocoon is intercepting all of the energy and re-radiating it solidly in the infrared. Look, that's 100 microns. So there's all infrared. A little bit older, we've got the black body from that central object, and then a huge whopping infrared excess from the dust around it. That is not the same kind of, this kind of hole. That, it turns out, is a giant absorption line. That's a 10 micron absorption line that comes from silicates in the dust. So that is a giant absorption line. But here, look, most of the energy is coming out in the infrared from the dust. By this point, though, most of the energy is coming out from the star. You still have a big disk, big infrared excess. But by these phases, almost all the energy is coming out from the central object, and there's really only a subtle infrared excess. So these are the names: class 0, 1, 2, and 3. This is where most of the accretion probably takes place. The mass of the envelope is about half of the solar mass. This is the shortest lived phase. Class 1 is probably the end of accretion. The envelope is probably only a tenth of the mass of the sun, a little bit 10 times longer than a class 0 phase. Class 2 is an optically thick disk. The disk is about a hundredth of a solar mass, 10 times longer than class 1. Class 3 is an optically thin disk, much less massive disk, 10 times longer than class 2. Now, those timescales are very, very rough, and Spitzer has changed those timescales a little bit. But the really important thing here is that those definitions are entirely empirical, and they are based entirely on the shape of the SED. The interpretation is the next logical step, but the shape of that SED is what's defining those classes. And then you get an additional perturbation that people start throwing in nomenclature. So class zeros are sometimes also called protostars. And then here you've got a rising SED, or here you've got a falling SED. And so then people said, well, there's got to be something flat in the middle, right? Because you got to go from rising to falling. So some people put a flat class in the middle. Originally, these things, before we had full SEDs, were called classical T-Tauri, because T-Tauri is the name of a star. And so other stars that look like T-Tauri were called T-Tauris. And then we discovered that there were like two kinds of these. And so classical T-Tauris are these kinds. And then weak line T-Tauris are similar but not the same. They have much less of an excess. Transition disks are these kinds of things in between, having a big infrared excess and a small infrared excess. And then debris disks are second generation dust, basically what happens when you get protoplanets colliding and creating a second generation of dust. All right, so as you've already guessed, nomenclature is a nightmare, because that physical interpretation of that classification definition being degree of embeddedness is a separate logical step, right? Because we're looking at the SEDs, and interpreting that as embeddedness is a logical step, and interpreting age is yet another logical step. Nomenclature is a nightmare. We're going to call all of these things young stellar objects. You can induce the other names. And then there's the classical T-Tauris and weak line T-Tauris and flat. We just talked about transition disks, debris disks. Okay. The idealized process strictly only applies to low mass stars. High mass stars probably do this too, only much faster. We just don't know because it's hard to catch them. Class zeros are the shortest lived phase, and so they're the hardest to catch in the act. It used to be that there were very, very few class zeros known, but Spitzer has found them in abundance. Same with class ones. Class zeros used to be defined as undetectable in the infrared, but that was a really poor definition even in the beginning. And again, the classification is based on the SED shape. So we'll be constructing these for each of the objects that we find to see which class they fall into. Although the story that we've spun here seems nice and well defined, it's complicated because you can find class 2s and 3s at the same age. So some stars are losing their disks quickly and some hold on to them for a long time and nobody knows why. It's not clear whether we can find class 0s and 1s at the same age. In part, that's because too few of them are known, but getting an age for them is really, really hard. A stars are more massive than these classes usually refer to, but I mean, I showed you this plot in the earlier movie, right? And you can see this is confusing, right? Because you've got very young stars that have no disk and some of the same age that have big disks. There's a lot of confusion. So it's also true that we can be fooled. You can easily imagine that a class 3 star that is edge on might look like a class 2 or even a flat. So it could be that some things that we think are the youngest protostars are just edge on older things. So it's hard. Most people just, when they say class 0, 1, 2, 0, 1, flat, 2, 3, they mean a series of youngest to oldest, but there's still this fundamental uncertainty. And how can you tell a transition disk as being different from debris disks? It's really hard. Some of it is an age argument. If you have spectroscopy, you can make arguments based on chemistry. It's hard. And then there was something called the transition disk wars, which was people were fighting over whether or not a transition disk evaporates evenly. In other words, disk disperses from the inside and the outside at the same rate, or does it disperse from the inside and then eventually disperses on the outside? It's confusing. And then there are these people in 2012 that found that some of these disks seem to vanish on very short timescales, which doesn't make any sense. I don't find that in my data, and I have a lot more stars, so it's confusing. For most of the stuff that we do in NITARP, most of the stars are probably going to be 2s because it's the longest lived stage of stars that still have an infrared excess. And we don't have an easy way to find stars without infrared excesses with the data that most NITARP teams work with. So this is an analogy that works better than it has really any right to. This analogy between studying star formation and imagine if you were an alien trying to understand how humans form and evolve. Or form and live, maybe is a better term. First of all, if you just picked a random spot on Earth, you're going to hit water. It's not going to help you understand humans. Just pick a random spot in space, you're not going to find a stellar nursery. If you just pick, if you're lucky enough to find ground, may or may not find people. If you're lucky enough to find people, you may or may not find a daycare center. You have to work hard to find a daycare center. And you have to work hard to find a stellar nursery. Even when you find a daycare center or a stellar nursery, it is hard to find the really, really, really young stars. It is really, really hard to find pregnant ladies because out of all of the phases of a human life, that phase in utero is the shortest phase of life. But when you find babies and toddlers, you often do also find pregnant ladies. So you can find babies in utero if you find babies and toddlers. Class 0s are hard to find, but you can often find them near class 1s. The time that you spend as a fetus is less than the time you spend as a baby, which is less than the time you spend as a toddler, which is less than the time you spend as a little kid, which is less than the time that you spend as a teen, which is less than the time that you spend as a young adult, which is less than the time you spend as an adult. Time you spend as a class 0 star is less than that as a class 1, which is less than you spend as a flat, which is less than you spend as a class 2, which is less than you spend as a class 3, which is less than you spend as a main sequence star. A fetus is still going to be enshrouded within the mother. Class 0 is still enshrouded within its nebula, within its cocoon. A baby or a toddler or a kid is noticeably, instantly, obviously different than other people. Class 1s, flats, and 2s are noticeably, instantly, obviously different than other stars because they have disks, they're rotating quickly, they have big flares and big spots. They're accreting matter. They're obviously really, really different. Teens and young adults are more subtly different. You may not be able to tell that they're different from other adults until you get up close. They might have more piercings and more tattoos. They might talk differently. But from a distance, they're indistinguishable from adults. Class 3s and young hydrogen-burning stars, again, look an awful lot like fully fledged adult stars. But they're more subtly different. They in general rotate faster, they're more active, they have more spots and flares. But you have to look more closely before you can see that they're different than older stars. See, I told you, the analogy works better than it has any right to. So this is my sad and pathetic PowerPoint version anatomy of a young star. It's not to scale. You've got this young, fully convective, low mass star in the center. And because it is fully convective and because it is rotating quickly, it has really, really strong magnetic fields. So the magnetic fields, are very, very strong. And so they actually thread the circumstellar disk around it. And those magnetic fields are so strong because when the disk comes in close enough to the star, it's going to heat up enough that it's charged, it's ionized. And the magnetic field is so strong that it's actually going to truncate the disk. And because the matter is charged, it's ionized, it's going to see the magnetic field, so then it's going to crawl up the field lines and crash down onto the star. And where those footpoints, those magnetic footpoints are, it's going to be a shock from all of that matter crashing down onto the star. So it can be a ring or a spot, it's not clear. But you get hot spots from the shock of where that matter hits the star. And because they are young and fully convective, you get big honking star spots. Now, remember, for the sun, star spots are pretty small, a couple percent of the star's surface, the sun's surface. For these young stars that are fully convective and very active because they're rotating quickly, you get big honking spots. I mean, like huge spots. Maybe half the surface is spot. So you get big honking flares and coronal mass ejections too, especially because there's big, strong magnetic field. And you've got the circumstellar disk too, which probably flares on the edges. So you get a lot of interesting light here too. You get X-rays from the flares, ultraviolet from the shock, emission lines from the accretion columns, infrared from the disk, mid-infrared further out, scattered optical light from the edge of the disk. And of course, all of this is changing all the time, because accretion is not slow and steady. It is likely catastrophic and big and really obvious. So this is a series of images taken from Hubble, about 1 frame per year. You can see it's an edge-on disk. You can see the flare. You can see the jets. You can see matter moving out through the jets. You can even, if you look, see a bright spot on the other side of the bowl that is this disk. That is probably scattered light. There's probably a spot on the star, a hot spot on the star that's rotating, and we're seeing scattered light off of the disk flare. This is a movie of another edge-on young star, but this one happens to be a binary, and we can't actually see the binary. It's completely embedded. This is another Hubble set of observations, but this is a binary that's so embedded that we can't actually see it. And they're orbiting each other there, and it's probably an elliptical orbit. And every time the binary, the pair, gets close, you end up with this surge of brightness, and you can see the surge of brightness moving out along the cavity carved out by a jet in the past, both above and below the disk. So this happens, this pulse happens every 25 days, because that's the orbital period of the binary. So very, very dynamic place. And when you start to incorporate rotation, which is a lot of what my research interests are, then it gets really complicated. So here we've got a young star that doesn't have a disk, and those green things are supposed to be magnetic field lines. When you have a young star that's contracting out of the way of the main sequence, it's going to spin up because it's getting smaller. So of course it's going to spin up. But when you have a disk around it, because that disk is ionized, it can't drag the magnetic field lines through the disk. So even though the star is contracting, it can't spin up. So you will end up locking the rotation of the star to the Keplerian rotation rate of the disk, where the magnetic field lines thread the disk. It's draining angular momentum through the field lines into the disk. And so the star doesn't change rotation rates. So that I have spent literally decades trying to solve this problem, trying to understand how this works. Really complicated. So out of all of these things, here are the most important things to remember. YSO is a young stellar object, and that refers to all of these young low mass forming stars. IRXS is the easiest way that we have right now within our NITARP projects of finding low mass young stars, given the tools that we have. But there are other ways to do it too. You can look for UV access or variability or X-rays. There's lots of ways to do it. The class 0, 1, flat, 2, 3 is an entirely empirically defined sequence based entirely on the SED shape. It's probably an evolutionary sequence, but it's complicated.